All right, we're on to the last topic in Chapter 3, additional topics involving probability and counting. Let's start with some counting things. So first off, a permutation is an ordered arrangement of n objects. The number of different permutations of n distinct objects is n with this exclamation point, which we read as n factorial. So basically, n factorial says start with the largest number and then decrease by 1 every time until you get down to the number 1. 0 factorial is equal to 1, just as a special note. And so if you look at the example 6 factorial equals, starting with 6, 5, 4, 3, 2, 1, multiplied together, and we end up with 720. 4 factorial would be 4 times 3 times 2 times 1 factorial as well. What's nice about this is we can find factorials on the calculator. There's an actual special button. So let's take a look at the calculator. So if we look at our calculator, let's do 6 factorial first, and then we'll find the answers to the others. So on the calculator, if we hit the math key, which is under the alpha key right here, probability has its own set of functions, so we're going to tab over until we get to probability. And if you go down, you'll notice that number 4 has that exclamation point. Now, what's a little bit trickier in this case is you actually have to put in the 6 first. So if we go back to the home screen, so second, quit. I want to find 6 factorial, so I'll have to hit the 6 button first, then hit the math key, tab over to the probability, number 4, and it shows up as 6 with this exclamation point. If I hit enter, I'll find out that yes, indeed, it is equal to 720, which is what we said it was right here. So 13 factorial. So again, we're going to hit 13, math, probability, number 4, and then enter. And it's that really large number. So you can see factorials are going to get quite large quite fast. And so the other one was, I think it was 10 factorial. So 10, math, over to probability, number 4, hit enter, and there's your 10 factorial. So just between 10 factorial and 13 factorial, the numbers jump very, very quickly. So if we write that down, 13 factorial was equal to 6, 2, 2, 7, 0, 2, 0, 8, 0, 0. I'll put my commas in place. This is hundreds, thousands, millions, billions. So this is 6 billion. So there are over 6 billion ways for this to happen. It's B with a B, billion. 10 factorial was 3, 6, 2, 8, 8, 0, 0. Again, I put them in. This is over 3 million. So the numbers are going to increase very fast as we continue to multiply that out. Also on your calculator, you can do this with just using the buttons on your calculator. So 13 factorial would be 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's a lot of multiplication, but if you forget where that button is on your calculator, you can certainly do this the long way. So 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 equals, and you'll see that it's the 62270200800. You can use the button. It's much better to use that button, but I know sometimes we forget where it's at. All right. So an example. It says the objective of the 9x9 Sudoku puzzle is to fill in the grid so that each row in each column and each 3x3 grid contains the digits 1 through 9. How many different ways can you build the first row? So I'm just going to look at the first row. Well, what it's saying basically is that the numbers cannot repeat. And so if you think back on this, this is sort of like we did when we talked about slot problems. And the difference with slot problems is not always do we decrease in order. But in this case, this would be like 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Because there are 9 slots, each number cannot be repeated. So it's very much like our slot problems. But rather than list it, because they do decrease in order all the way from the beginning number at 9 all the way down to the last number of 1, that would be the same as doing 9 factorial on your calculator. And 9 factorial on your calculator is 362880. All right. So what makes permutations a little bit different and gets us away from slot problems is now it says find the number of permutations of n distinct objects taken r at a time. And again, order matters. So the order we put these in definitely matters. And if so, here's the formula. So we're going to take n factorial, and we're going to divide it by n minus r factorial. And again, there is a button on the calculator, so we can use the calculator. Which is nice. We do want to use the calculator. So it asks, first example, find the number of ways of forming 4-digit codes in which no digit is repeated. The number of ways that we can form 4-digit codes with the no digit repeated. So if we again look back at this as slots, remember that we had 10 times 9 times 8 times 7. This does not go all the way down to 1, so I cannot use 10 factorial. 10 factorial is not an option here. But because the codes differ, because nothing is repeated, if I use this new formula, it says the permutations of 10 things taken 4 at a time is equal to 10 factorial over 10 minus 4 factorial, which is equal to 10 factorial over 6 factorial, which, if we write this in longhand notation, this would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over, there is a times 1 here on the end, over 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And if you do, because we're dividing, we know that the 6 here cancels, the 5s cancel, the 4s cancel, the 3s, the 2s, and the 1s cancel. What do I end up with? Exactly the same thing. The 10 times 9 times 8 times 7 which is equal to 5,040 in this case. So it's like similar to slot problems, but this time we just can't go all the way down to times 1. So we have to look at how many different positions we're looking at. So it's n distinct objects taken r at a time. How many positions are we looking at? So number 2 says, each year 33 race cars start the Indianapolis 500. How many ways can the cars finish first, second, and third? So first, second, and third. Order here matters, and that's going to become very, very important. So for permutation, order matters. And if you're not sure whether order matters, then again, think about this. In this case, it's really easy to think about, because if you're talking about first, second, and third, do you think there's a monetary difference between first, second, and third? You think it matters if you finished first versus third? Well, you better believe it matters. So order definitely matters. So this would be permutation, 33 race cars. The only thing we're interested in is the first 3 positions. So taken 3 at a time. That would be 33 factorial over 33 minus 3 factorial, which is 33 factorial over 30 factorial. Now I'm going to do a real quick shortcut. That would be 33 times 32 times 31 times 30 factorial divided by 30 factorial. Well, we know 30 factorial is 30 times 29, 28, 27, all the way down to 1. So these two will indeed cancel. And I end up with 33 times 32 times 31, which is 32,736 ways. So if you're betting on this, the chances that you guess the exact right way would be 1 out of 32,736. And yes, it is very similar to slot problems. So in some cases, you won't need to do the permutation. In some cases, the slot problem will make more sense to you. I don't care how you do it, but we'll show you some in just a minute that are a little different. All right, so how do I use the calculator? So let's do the 33 race cars, taken 3 at a time on the calculator. To do that on your calculator, you do have to enter the 33 first. So you're going to enter 33 first. And then you're going to hit the key buttons. So in this case, if I hit $33, then again it's still under the math key. It's still under the probability functions. This time, if you'll notice, number 2 is NPR. Now be very careful because we are going to look at NCR in just a minute. So NPR is number 2. So 33P3, and then hit enter, and that gives us that 32,736. The same if we had done 33 times 32 times 31. Same value. So it's going to be hit 32, I'm sorry, 33, then the math key, and then after you hit the math key, you're going to go over to the probability key. After you go over to the probability key, you're going to hit number 2 for NPR. After you hit the NPR key, then don't forget to close off by hitting the next digit, which in this case was a 3. So when you're done on your home screen, you should see exactly the permutation that you want. You should see exactly the permutation that you want. 33P3. Okay. All right, so now it gets a little bit different, because now we're going to talk about still a permutation problem, but this one is called a distinguishable permutation. And distinguishable permutations say that we have the number of n objects, where n1 are of one type and 2 is of another type, and so on. So the best way to describe this would be if you're looking at, again, order matters because it's still a permutation. So because it's a permutation, order matters. But then, this time it's distinguishable order matters. So in other words, if I write the numbers, if I have the following numbers, and I want to know how many different codes I can make from this, well then 3, 4, 3, using it 3, 4, 3, is the same as, in reverse order, 3, 4, 3. So they look the same. And if they look the same, then they're not distinguishable. So we want ones that look different. So when we have repetition here, and the 3's repeat, that's where this part comes in. These are repeated values. So first example, a building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. How many distinguishable ways can the houses be arranged? So what this is saying is that you don't want the same house next to each other. Basically is what you want. So you can have, so no 2 houses next to each other. So no 2 houses next to each other. Okay. So how do we determine that? Well, we have 12 total houses. There are 6 one-story, 2 two-story, and 6 split-level houses. So we don't want them to be next to each other. I guess it should say no 2 of the same type of houses next to each other. So we're going to have n factorial over each one of these houses. So there's 6 one-story. So there are 4 two-story and 2 split level. So these are the 3 distinguishable houses. So that's going to be n1 factorial, and 2 factorial, and 3 factorial. This would be the first one, second one, and third one. So when I put the formula together, it would be 12 factorial, so there's 12 total houses, divided by 6 factorial times 4 factorial times 2 factorial. These are multiplications in between. We don't write them as multiplication, but we are multiplying here. It's just the definition is multiplication. And it sort of gets lost in here. There's the little multiplication symbol. So we could do this without a calculator, simple enough. It would be 12 times 11 times 10 times 9 times 8 times 7 times 6 factorial divided by 6 factorial. Because it's multiplication, I can put these in any order I want. So that's going to be 4 times 3 times 2 for the 4 factorial. And then 2 times 1 for the 2 factorial. And doing the secret magic stuff with the math. The 6 factorials cancel out. Here I have 4 times 3, which is 12. We cancel with this 12. 2 goes into 10 5 times. 2 goes into 8 4 times. And this is really cheating. Not cheating, but it's sort of shortcutting it. So I would have 11 times 5 times 9 times 4 times 7. Using my calculator, I end up getting 13,860 different ways. Would you ever do it by hand? Probably not. You also don't have to do it by canceling these things out. You can do it by simply using your calculator and multiplying out the numbers, 12 times 11 times 10, and then on the bottom for your denominator the same way. You have to be very careful because you do have to use parentheses in this case. So if I'm going to use my calculator, and it's fine to use the calculator, I just have to, again, make sure I'm using the calculator correctly. So I want the whole entire numerator in parentheses and the entire denominator in parentheses. So that would be 12 factorial, 12, and then the math key, and then over to probability, number 4. There's 12 factorial divided by, and then I have 6 factorial, 6 math probability 4 times 4 math over to probability number 4 times 2 math over to probability number 4, and then close my parentheses and then hit enter, and I do indeed get the 13,860 ways. Again, your test day is not the time to practice your calculator. Do practice your calculator as you're using your MyMathLab or as you're doing homework. Make sure that you are practicing with your calculator. The calculator will give you a wrong answer if you input it wrong every time. So be very cautious of that. Okay. So again, on your calculator, it's going to look like 12 factorial on top divided by 6 factorial times 4 factorial times 2 factorial. And that should give you the same answer. And again, I am not suggesting you do it by hand, but I am saying if you don't have a calculator that day and you want to make it a little easier on you, you can certainly do that. Also, if you don't have a calculator that's got the factorial button, you're going to have to do this by hand, or at least the longer way, 12 times 11 times 10 times 9, and so on. All right, and then that's going to take us to what's called a combination. The number of combinations now is of these same n objects from a group, are objects from a group of n items, and the difference is this time there is no regard to order. So for combinations, order does not matter. The formula is very similar. We have n factorial divided by the n minus r factorial, which looks very much like permutations. But you also divide out the r factorial. So you're dividing out where the order matters. So now these combinations are smaller options because you've divided out what happens in the order. So a State Department of Transportation plans to build a new section of interstate highway and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from 16? How many different combinations of the 4 companies can be selected from the 16 companies? So think about now, does order matter? Well, let's just say out of the 16 companies, they're going to choose company A, B, C, and D. It's not tied to a position this time like the race cars were. So it doesn't matter if company A gets the first bid or if company B gets the first bid. So company A getting the first bid doesn't matter because they're still all 4 getting the bids. Likewise, company D could be the first one. Same, 4 companies getting a bid. The order that they get those bids in does not matter. So some of the things for combinations would be things like committee work or juries. It doesn't matter the position that the 12 people sit in the jury, it's the same 12 people. Same thing with committees. It doesn't matter where they sit in the room, it's one committee made up of the same people, no matter where they sit. Now, if we're asked about president, vice president, and say secretary, yes, order there does matter because, again, tie it to money. Do you not think a president would make more money than a vice president? Maybe not in the one you're building, but certainly in general, that's possible. Right? So this time we have the combination of 16 companies, of which 4 will be selected. Using the formula, that would be 16 factorial over 16 minus 4 factorial times 4 factorial. So that would be 16 factorial over 12 factorial times 4 factorial. And again, if you did it this long way, you could put this on your calculator. You could do it out the long way, 16 times, or 15 times 14 all the way down. Or you could also use your calculator. So if you're going to use your calculator, again from the home screen, make sure that it looks like 16C4 when you're done. So on your calculator, you would type in 16 first, then back to the math probability key. Number 3, I told you we would use that C key, so number 3 is your combinations. And see how small the numbers are as well, so that's 16 things, combination-wise, taken 4 at a time. Hit enter. And now there are only 1,820 ways that the companies can be selected. 1,820 ways. So a lot fewer ways when order does not matter because you're taking out the order. Basically, that's what the extra division is doing, is taking out that order. All right, so let's just look at some problems in general and see what we're after. So number 1, a student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve on any of the positions. What is the probability of randomly selecting 3 members who will be chosen for the board? Right? So, do you think order matters? And the answer would be yes. Order does matter in this case. So this would be a permutation. So even though you may not think there's money tied to it, do you think that the person who serves as the chair will have a very different job than the webmaster? And the answer is yes. So you don't, to order that they are sitting in those positions matters as well. So there would be 17 members. It's a permutation. There are 3 positions being filled. So that would be 17 factorial over 17 minus 3, which is 14 factorial. If I multiply that out, I end up with 4,080. And that's 4,080 ways to select the people. Now be careful because the question says, what is the probability of randomly selecting that person? What is the probability? So the probability then is the probability of selecting these people, selecting this group or this order position would be 1 over 4,080 ways, which is 0.0002. So if you're one of those members and you're afraid of getting selected, well, the chances of you getting selected at that point are very small into a specific position. So instead, what if it were a subcommittee made from 3 of the 17 members? How is that different? Well, again, this is a committee. The way they sit around the table does not matter. So this would be a combination where order does not matter. And if order does not matter, then I have 17C3, which would be 17 factorial over the 14 factorial times the 3 factorial. And I'll take out the repeating ones. In which case, if I did this, I would end up with 1,287 ways, which is way fewer than the 4,080. Because that order is important, because it matters whether Jane is serving as the chair, John as secretary, and the webmaster is Jim. Where here, Jim, Jane, and John can sit around the table and it doesn't matter what order they sit in. Again, I know some of these can be confusing, so just practice. All right. Next example says, find the probability, so we're going to find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. So, because these 5 diamonds can be in any order, this is going to be a combination. Again, order does not matter. However, I do have to think of this in 2 ways. So the first thing I'm going to do is find the number of combinations. So the number of ways 5 diamonds can be picked. Right? So 5 diamonds can be picked. Well, that's going to be the combination. We want 5 diamonds, so that's going to be the 5. But how many diamonds are there total in the deck? Well, in the deck of cards, there are 13 diamonds. So if I did C13, 5, that would end up being 1,287. Uh-oh. I think I confused problems. Yeah, this is not the correct answer here. Let's see if I can find the correct answer. So let's do it on the calculator. So that would be 17 and then math, probability, number 3, 17C, 3 is 680. I'm so sorry. This is 680 days. So even fewer. Sorry, my answer key didn't have the right answer there. I apologize. All right, so back to the diamonds then. So there will be 1,287 ways to get 5 diamonds. In any order, because remember, diamonds, order doesn't matter. Then, for number 2, I need the number, because I'm doing probability. Remember, probability has to be over the total number. So in part 2 is going to be the number of ways any 5 cards can be chosen. So any 5 cards. That's going to be a combination. Order still doesn't matter. Doesn't matter how I hold those cards in my hand. So it's going to be the combination. I still want 5 cards. But this time I have 52 cards to choose from. So there's 1,287 ways to get 5 diamonds. There are, if I do this correctly, carefully on your calculator, you only want to use a calculator obviously for this one. It would be 2,598,960 ways. So if the problem just asked how many ways can this happen, you would be done. Again, there are 1,287 ways to get 5 diamonds. There are 2,595 ways to get any 5 cards. Any 5 cards. But this problem asks for the probability. So the probability that this happens, would be probability that we get all diamonds would be the 1,287 hands with 5 diamonds divided by all the possible hands that we have. And that would be approximately 0.0005. So not very often. So if you ever played poker before, the chance of getting 5 diamonds dealt to you, 5 diamonds, is not very, doesn't happen very often. Now there's more to it because oftentimes in poker you get to draw cards and there's more to it. But just in general, if you were given 5 cards, the chance that they would all be diamonds happens very, very infrequently. It's 5 10,000ths of a time. Tenths, hundreds, thousands, 10,000ths. So this is 5 out of 10,000 hands. So it would only happen 5 out of 10,000 hands. Not often. All right. Next one. A food manufacturer is analyzing a sample of 400 corn kernels for the process of a toxin. In the sample, 3 kernels were highly dangerous toxin. 4 kernels are randomly selected from the sample. What is the probability of exactly 1 kernel containing a highly dangerous level of toxin? So this is a much harder problem, so we have to be very careful and map this out. We are looking for the probability. Since we're looking for the probability, we have to then say how many ways are we going to find each piece. So part 1, well, first we need to decide, does it matter whether order matters or not? And in this case, order does not matter. So this one is a combination. So order does not matter. Okay. And again, how do I know for sure order doesn't matter? Well, it's going to kill you regardless of whether you eat the first kernel or the fourth kernel. It doesn't matter. So order does not matter. So the first thing, you need the number of ways 1 out of 3 kernels can be chosen. I guess we should say 1 out of 3 toxic kernels can be chosen. And that's pretty simple. That's going to be C31. Number 2 is going to be the number of ways to choose 3 non-toxic kernels. Well, there are 3 toxic kernels out of a sample of 497. So that means that there are 397 non-toxic kernels, of which we're going to choose 3. So we're going to choose 3 non-toxic out of the 397 that are not toxic. Right? So why did we choose 3 here and 1 here? Because remember, we are choosing 4 kernels at random. We want only one to be toxic. But we're still choosing 4. So that's why 3 plus 1 is 4. So the third step then is going to be the number of ways to choose 1 toxic and 3 non-toxic together. So again, in the first one, we chose 1 toxic. Here we chose 3 non-toxic. Now we want to do 1 toxic and 3 non-toxic. So using our AND statement, that would be 3C1 times 397 C3. And if I did this on the calculator, and you might want to use parentheses on the calculator just because it separates it a little nicer. You don't have to as long as you're doing the multiplication. If I multiply these out, there are 31,049,370 ways to choose that combination of 1 toxic, 3 non-toxic. Not quite done yet. So number 4, then, remember, we're still trying to find probability. Now, probability means this is the number of ways to choose the experiment. Now I need the number of total ways. So number of total ways to choose the number of total ways to choose any 4 kernels from the 400, I won't say batch, from the 400 sample. That's a better word. So again, it doesn't matter the order you pick. At the end of the day, you got 4 kernels in your hand, and it doesn't matter where they sit in your hand. There's still 4 kernels. So this would be the combination of 400 things taken 4 at a time, which is 1,050,739,900. So the last step, almost done. So the last step, step 5, is finding the probability that you have 1 toxic. 1 toxic and 3 non-toxic. Because 1 toxic implies 3 non-toxic. And so we would have 31,049,370 divided by 1,050,739,900. That's going to be approximately 0.30. Oops, I'm sorry, 0.030. 0.030. So that's about 3% of the time. I'm not sure I'm willing to risk having a toxic piece of food 3% of the time. That's 3 out of every 100. That's 0.03. We read that as 300. So 3 out of every 100 times you choose 4 kernels. So you grab into the batch, grab into the sample, you pick 4 kernels of corn. 3 out of 100 times, at least one of them is going to be toxic. So that's not very good odds. It'd be 1 out of about every 33 1/3 choices. All right. Well, that concludes this last section. It also concludes chapter 3. And so you should be able to get through the rest of your homework and the rest of your assignments without too much issue. Text me if you have questions. Or email me, I guess, if you have questions.